Hello and welcome to Mechanical Y. Today we're doing a micro lesson on radians, specifically what is a radian and what is it used for. In short, a radian is a measure of an angle, much like degrees. But why would we represent the corner of a room as pi over 2 radians instead of 90 degrees? For those of you who don't have a strong STEM background, radians seem a bit peculiar and odd to use. However, once we look into what a radian is and what it represents, it'll become clear that it is actually a very useful way to represent angles.
Okay, let's start with a circle. Now this circle has some radius r. Now let's say that this radius makes an angle with some reference line, and let's call this angle right here theta. So what do we notice? We notice that as r swept up from this reference line, it created this angle, but it also, the tip traveled some distance across the perimeter of this circle. And let's call this distance traveled S. Now we notice as we sweep from this reference point, not only does the angle swept to get bigger, but so does the distance traveled around the edge of the circle. So we can say that the distance traveled is proportional to the angle. For those of you not familiar with it, this is a symbol for proportional. So we can say that the distance here, S, is proportional to the angle theta. So let's take an example. Let's say that we sweep 1/6 of the way around the circle. So we start here and we travel 1/6 of the way around the total way around the circle. So we can rewrite this as theta is equal to 1/6 of the circle. So now to calculate the distance traveled, we know that S is equal to 1/6 of the total circumference of the circle. So if we sweep 1/6 of the way around, this angle is 1/6, and we've traveled 1/6 of the way around the circumference. And the circumference is usually given as C. Now we know that the equation for circumference is equal to 2 times pi times r. So the distance we've traveled around the edge, if we sweep 1/6 of the way around the circle, is 1/6 times 2 pi r. Now this we can simplify, and it comes out to pi over 3 times r. Let's say we sweep some other angle from this reference point. Let's say we go around, let's say 5/8 of the way. So we sweep 5/8 of the circle. And we could write this as theta is equal to 5/8 of the circle. So now we could do this just like we did before to calculate the distance traveled. So if I travel 5/8 of the way around the circle with the angle, how far did I travel around the perimeter? The answer is 5/8 of the circumference, which is equal to 5/8 times 2 pi r, just like before, and this simplifies to 5 pi over 4 times r. And here we start to notice a pattern. First we notice that if we travel by some angle, here and here, then the distance, S, is traveled when we sweep by that angle is equal to the radius r multiplied by some number. And this number here is always proportional to the angle swept multiplied by 2 pi. So this represents the angle. And we're going to define this as a representation of the angle in radians. So now we can write this equation in a general form to say that the distance traveled around the perimeter is equal to the angle swept here, given in radians, times the radius of the circle r. And this is a definition that we could use to define what a radian is. So how is this useful? Well, let's take an example. Let's start with a circle. And this circle represents a wheel that is sitting on the ground. And this wheel has some radius, r. And let's say it rolls forward. It rolls in this direction. So what happens? Well, the wheel will end up here at some later time, and we'll notice that this radius r has moved up to some new point relative to its reference position here. So it has now created an angle of theta. So how far has this wheel traveled? Well, we know from this equation, if this angle is given in radians, then we can calculate this distance traveled around the perimeter as s. Now we know that as a wheel rolls, this part s represents how far it's rolled. So the distance the wheel has rolled forward is also equal to s. So radians give you information about angles and distances. And this is very convenient. If you were to represent this as degrees, you would have to do some more mathematical computation to figure out how far this wheel has traveled. Now, radians does have one additional benefit, and that's computation. Using radians is actually very convenient in certain mathematical expressions. It actually works out much simpler and much easier to give certain mathematical expressions in terms of radians and not degrees. So radians do have many benefits when compared to degrees.
So if radians are so convenient, they give you information about angles and distances traveled, and they work out so well computationally, why do we even use degrees at all? And why 360 degrees around a circle? Why not 100 degrees, or 1000 degrees, or 258 degrees around a circle? Why 360? Well, part of it is historical precedent, but we continue to use 360 because it is a very convenient number itself mathematically. You see, 360 has 24 divisors, which means if I was to break up 360 into equal groups of whole numbers, then I could break it up 24 different ways. 360 is also divisible by every number between 1 and 10 except for the number 7. By comparison, the number 100 only has 9 divisors, and the number 1000 only has 16 divisors. So being able to divide 360 into a large number of groups of equal whole numbers is very convenient. For instance, a right angle is exactly 90 degrees. If I was to slice a pizza into 8 equal slices, each slice represents 45 degrees. And if I was to break up the Earth into 24 time zones, each time zone would be represented by exactly 15 degrees of longitude. When dealing with radians, you constantly come across the number pi. And pi is irrational. I can't have pi dollars in my bank account, and it's very hard to precisely measure pi inches with a ruler. So when you have to deal with whole numbers and break things up into whole even groups, then degrees can still be very useful and very intuitive to work with. Well, I hope you found this interesting. If you did, please like and share this video, and please subscribe to stay up to date on future micro lessons.